Starting chapter 14 today, we're going to talk about line integrals. So in the middle of my screen, you can see that integral. It says area equals the integral with a subscript c f of x, y, ds. So this is a line integral. So f of x, y is the red surface you see over on the right. And c is that curve that I've got drawn in R2 over on the left. And that curve is copied on the XY plane on the floor over in R3 on the right. And this particular applet has these draggable points over here. So I'm going to drag some of these points. And you'll see, however, I change the curve over here on the left, it changes it over on the right in R3. And what it's drawing for us in purple is sort of a curtain that's hanging down, or a fence that's following the curve in the XY plane, and its height is determined by the surface. And so these line integrals we're going to calculate is going to calculate the area, so like the length times width, two-dimensional area of that curtain or that thin paper that's tracing that curve down in the XY plane. So these line integrals are going to calculate the area of that purple curtain that's hanging down from the surface in R3. And that purple curtain is defined by a couple of things. The shape of the curtain is determined by some curve in the XY plane. And that's what the C in the line integral notation is referring to. It's referring to a curve in the XY plane. And we saw in the applet how we could change that curve and it would change the shape of the curtain. The other thing that defines this curtain is the surface itself. The f of xy tells it how high it's supposed to be at any given point. All right, so f of xy is going to tell you how high, or the length of that curtain at any point. All right, so the way we're going to calculate the area of this curvy curtain is similar to what we do in Calc 1. When we had area underneath a curve, we would slice up that area into little bitty slivers. We're going to do the same thing here. We're going to slice up that curve into little bitty slivers, and then the height or the length of those little bitty slivers is going to be given by the function value f of xy. And then the ds, kind of like the dx in Calc 1, is just a width of one of those tiny little slivers. And ds follows that curve as we go along. So this is the width of a slice. This is the width of the slice. And then, of course, the integral, like integrals always do, will add up all of those length times widths to give us the area. Right, so how do we get our surface, our f of xy, to follow along that curve that's drawn in the xy plane? We're going to do this by parameterizing the curve C. So we're going to come up with a 2D, an R2 parameterization for the curve. So we'll represent it as a vector valued function. We'll have a function for x and a function for y, and then we'll have some limits on t. So we'll say like t goes from a to b. And then once we have this parameterization, we're going to rewrite our function f of xy in terms of that parameterization. So we're going to take our integral. Instead of x, I'm going to write the parametric equation for x, which is g of t. And then instead of y, I'm going to write the parametric equation for y. And then we'll integrate from a to b. ds, the width of that little slice, that's going to be represented by this. And that is the vector notation version of the arc length formula that you may have learned in your Calc 2 class. If you don't remember it, or if you never learned it, just trust me that that's going to calculate the teeny tiny slice width of one of those rectangular slices of the curtain. All of this integral has been rewritten in terms of t, so we're going to integrate with respect to t. And in the next video, I'll actually do an example of calculating one of these line integrals.